Picture this. Two dead stars, each heavier than our sun, but squeezed into the size of a city, are locked in a death spiral. They get closer, closer, until bam, they collide. The impact is so violent it crushes matter beyond atoms, beyond even protons and neutrons. And what happens next has physicists sweating. They call it a merger. We thought we knew the rules of the universe. Turns out, the rule book has some wild footnotes. Today, we're diving into 3 ways neutron star crashes are stress testing the laws of nature. First, a quick primer. When a giant star dies, its core can collapse into a neutron star. Imagine taking our entire sun and packing it into a sphere just a few miles across. A single teaspoon of this stuff would weigh 1 billion tons. When 2 of these cosmic relics orbit each other, they radiate energy as gravitational waves, those ripples in space-time Einstein predicted. This causes them to spiral inward, inevitably leading to a catastrophic collision. This smash-up does 2 incredible things. First, it shakes the very fabric of space-time so hard that we can detect the ripples here on Earth. Second, it forges the heaviest elements in the universe, like gold and platinum, in a brilliant explosion called a kilonova. This is the only event we know of that gives us both light and gravitational waves. A full-spectrum physics lab in a single fleeting moment. So you might have heard people say that neutron star mergers are breaking physics. But are they really? Not quite. What's actually happening is we're witnessing nature at extremes we can barely even model. We're talking densities higher than an atomic nucleus, magnetic fields that literally twist space-time, and temperatures so hot they could vaporize elements we haven't even discovered yet. Our models, they're cracking under that pressure. The laws of physics themselves, they're holding up just fine. It's our understanding of those laws that desperately needs an upgrade. Let's look at the first broken rule: gamma-ray bursts, or GRBs. The simple rule we had was that GRBs come in 2 flavors. Short bursts, lasting less than 2 seconds, were thought to come from neutron star mergers. Long bursts came from the collapse of massive stars. It was a neat, clean categorization. But then, the collisions started showing us something different. Some mergers produced gamma-ray signals that lingered for way too long, blurring the line between short and long. Others had strange delays between the gravitational wave signal and the flash of gamma rays. So why is this weird? Well, if the merger instantly creates a black hole, what's powering the engine for a prolonged burst? And if there's a delay, what's holding the jet of energy back? Is it messy, tangled magnetic fields? Or maybe leftover debris from the collision is choking the jet at the poles? Think of it like this. Imagine you know that sedans have short horns and trucks have long horns. Then one day, you hear a sedan honk for 5 straight seconds. You don't throw out the entire concept of sedans. You pop the hood and ask, what's going on in there? So, is the rule broken? Not really. The rule was just a shortcut. Reality, it seems, has a lot more dials and switches than we thought. Now for our second rule break. Things moving faster than light. The one non-negotiable rule from Einstein is that nothing can travel faster than the speed of light. Period. But when we observe the afterglow of a merger with radio and X-ray telescopes, we sometimes see blobs of matter that appear to be flying away at 3, 4, even 5 times the speed of light. This is called superluminal motion. So, have we finally broken Einstein's ultimate speed limit? Nope. It's actually a clever illusion. Here is how it works. The jet of material is blasting out from the merger and heading almost directly towards us at, say, 99.9% the speed of light. Now, light from the material when it's farther away has a longer journey to reach our telescopes. As the jet moves closer to us, the light it emits has a shorter trip. From our perspective, the later light signals almost catch up to the earlier ones. This makes the entire sequence of events look compressed in time, creating the illusion of faster-than-light travel. The material isn't actually breaking the speed limit. Our view of it is just distorted by a combination of geometry and relativity. It's like a train racing toward you with its headlight on. The light itself doesn't speed up, but because the train is closing the distance, it appears to arrive faster than if it were standing still. So, relativity isn't broken. In fact, it perfectly predicts this illusion. Seeing it just confirms that these jets are incredibly fast and aimed right at us. Finally, the third puzzle. What are neutron stars actually made of? We know it's ultra-dense matter, but how does that matter behave under such extreme pressure? Physicists use something called an equation of state to describe this. Basically, a rule that tells us how squishy or rigid the matter is. Is it stiff, resisting the crush, or is it soft, squishing down easily? But when we look at the data from mergers, we get conflicting answers. The gravitational waves we detect before the collision suggest the stars are puffy, which points to a stiff equation of state. But the light from the Kilonova explosion afterwards suggests the debris is surprisingly dense, which favors a soft equation of state. Both can't be right with our current simple models. This is weird. It's like squeezing something that acts like a sponge, then suddenly acts like a rock, depending on when you look. This tells us our understanding of matter is incomplete. Maybe there are exotic particles or even cores of quark matter hiding inside. Or perhaps the sheer chaos of the collision itself, with its intense magnetic fields and wild rotation, is scrambling the signal. The rule wasn't broken. The rule was just too simple. It assumed matter behaves one way. Reality is telling us that matter behaves in very different ways, depending on pressure, temperature, and spin. So, here's the real story. Physics isn't breaking. Our models are learning, and they're learning fast. We built our theories based on experiments we can do here on Earth. Neutron-star mergers are nature's own particle accelerators, cranking up the density and energy to levels we can only dream of. They're showing us what happens when you push matter to its absolute limit. And with every new piece of data, our theories grow stronger and more nuanced. That's not failure. That's science at its best. These collisions are the ultimate stress tests for the laws of nature. And whenever a rule seems to bend or break, it's a sign that we're about to discover something new and wonderful about our universe. Thanks so much for watching. If this video made you rethink what it means to break the rules, hit that like button and share it with someone who loves a good cosmic mystery. Let me know in the comments which of these puzzles you'd like to see a deep dive on next. And done.